Learn how to apply the limit laws to solve different limit problems. There are 7 different limit laws. To use all of these, we're going to first suppose that a and k are real numbers. So some integer values may be irrational coefficients, but a and k are 2 real numbers. And that the limit as x approaches a of f of x exists and is equal to L, where L is going to be some real value. And the limit as x approaches a of g of x exists as well and is equal to this value, which we're going to call m. And we're going to take advantage of the fact that we already have 2 limits that exist on 2 different functions, f of x and g of x, and see what happens, how can we combine those functions together, and will we still be able to take limits. So the first limit law is called the sum law, which says if I take the limit of the sum of 2 functions, so I have the limit as x approaches a of f of x plus g of x, that would be the same thing as taking the limit of each function separately and then adding those answers together. And since we know that the limit as x approaches a of f of x equals L, so since we have this piece of information, and we have the fact that the limit as x approaches a of g of x is equal to m, then by separating this in the limit law, I know that if I take these 2 limits, which each exist on their own, and add them together, then that will be the same thing as doing L plus m, since the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m. And we can do this since we can basically distribute a limit over a sum of 2 functions. The difference law is very similar to our second law here, and instead of summing 2 functions together and having f of x plus g of x like we did in the first law, we now have the difference of them, so f of x minus g of x, and it works very similarly. Instead of doing the limit of the difference, I can separate that and do the limit of f of x minus the limit of g of x separately, and that, since both of those limits exist, that would be equivalent to doing L minus m, since the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m. Now our third law we have here is the constant multiple law, which says if I have the limit as x approaches a of k times f of x, well remember k, that value right there, is our real number from the beginning, so it's some scalar, it's a coefficient on this function, that k actually has no effect on our limit. This would be equivalent to taking that constant outside and in front of the limit and going k times the limit as x approaches a of f of x, which would be equal to k times L, since of course in this case we know that the limit as x approaches a of f of x is equal to that L. So what our third law ultimately tells us here is that if I have a scalar or a coefficient, the limit has no effect on that, and if I can still take the limit of the function, then I can do that separately and then multiply by that scalar. Now the fourth law looks similar because I still have a product. The difference here is I actually have 2 different functions again. So I have the limit as x approaches a of f of x times g of x. So I have the product there of 2 different functions. And what I can do is similar to what we did in the sum and difference law, is I can take the limit of the first one, so the limit as x approaches a of f of x on its own, then multiply by the limit as x approaches a of g of x, and since each of those limits individually exist, and we know the limit as x approaches a of f of x is going to be equal to L, and the limit as x approaches a of g of x is equal to m, that is equivalent to having L times m then. So really 1, 2, and 4 kind of go hand in hand there with addition, subtraction, and multiplication. And then 5 is going to group in with those with division. So if I have the quotient law here, which says the limit as x approaches a of f of x divided by g of x would be the same thing as doing the limit as x approaches a of f of x individually in the numerator divided by the limit as x approaches a of g of x in the denominator. And since each of those limits exists, and we know that the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m, then this would be equivalent to saying L divided by m. What's important to note here is that we do have to have the restriction here that our denominator cannot equal 0, otherwise I would not get a well-defined answer. So we do have this extra condition here that says where the limit as x approaches a of g of x, so our denominator down here, which was equal to m, does not equal 0. And just the reason being is we can't divide by 0 in math and get a valid defined answer out of it. So if you've had me in class before, you know that or maybe this will help remind you, is I have that sign above both of my doors that say divide by 0 with the question mark there, and one of them says okay, where I have 0 over a non-zero number k. That is okay to do. In that case, we would get 0. And then the other one says no, where I have n over 0, because if I have 0 in the denominator, I cannot do that. I would not get an answer. Instead, I would get a value that is undefined. So this is why we have to have that extra restriction here for the quotient law. Okay, the power and the root law kind of go hand in hand together as well. So I'm going to group those two together. The power law says if I have the limit of a function raised to a power, that would be the same thing as instead of having the power inside the limit, I could do the limit of the function all raised to the power. So the difference here is that in the first one, the n is just raising the function f of x, versus now it's the same thing. What the power law tells me is that's the same thing as doing the limit as x approaches a of f of x, all raised to the n. And since we know that that limit as x approaches a of f of x is equal to L, then this would be the same thing as saying L to the nth power, where n is any positive integer. And of course, technically this works if n is equal to 1, but it's kind of silly if n is equal to 1. So we would probably assume that n is greater than or equal to 2, just so we get something exciting here. Now the root law follows suit, and instead of doing a power, it's doing a root. So this is an nth root of x. So as a little kind of refresher over here, remember if I have the n up here, we call that the index. So I have my index of my radical. This would be pronounced the nth root of x. So this could be, for example, a square root. So if I have an index of 2, we don't usually write it, but that would be considered a square root. If I have an index of 3, I'd have a cube root. An index of 4 would be a fourth root, and so on down here. So we are assuming again that n is a positive integer, but particularly n is going to be greater than or equal to 2. So I'm starting with the square root. And this works similar to the power law. So if I have the nth root of f of x, so in the first statement here, I just have the radical over the f of x. That's the same thing as pulling the radical out and taking the entire nth root of the limit as x approaches a of f of x. And since we know that this limit is equal to L, then that's equivalent to saying the nth root of L then. And then this notation over here is just the definition of what an nth root is in terms of an exponent. So remember, the nth root of anything is the same thing as that piece to the 1 over n power. So over here in kind of our review section of notes, this would be the same thing, is instead of writing the nth root of x, that would be equal to x to the 1 over n power. So I have my radical form on the left to my exponential form on the right. Now, some of these laws might seem a little silly to you, like, well, of course I would want that to happen, but all this stuff doesn't always hold true for different concepts that we talk about in mathematics. For limits, this will hold true, and as we go through here, we'll talk about, well, how is this going to work if I have a derivative or if I have an integral, as we keep going. So let's look at our first couple examples here. So they say compute the following limits using the limit laws. So if you've studied limits before and you've had practice with them, you might be thinking, well, I'm going to do a direct substitution and be done with it. Well, right now we don't understand how to do direct substitution, and the way we actually get to do direct substitution is through the limit laws. So in this whole set of notes, we're going to really go through and make sure we're justifying and showing all of our work as we do each one of these problems. So I'm going to very carefully write out all the limit laws as we're applying these, which you might find a little silly, maybe even a little ridiculous right now, but it's really important to have the fundamental stuff down and how I can justify and work through these problems and why that is actually true. And that's what this section is about, is understanding why we can really do direct substitution through the limit laws. So our first example says the limit as x approaches 5 of negative 7x plus 11. So I notice a couple things here. I have an addition, so I'm going to end up using the sum law, and then I also have a coefficient here on the x, which means I can use the constant multiple law. So I'm going to first use the sum law, and I can break this apart as the limit as x approaches 5 of negative 7x plus the limit as x approaches 5 of 11. So this is here using the sum law by breaking it apart into my first function, which was the negative 7x, plus the limit of my second function, which is 11. From here, the limit of 11 I'm able to take, but the limit of negative 7x, I need to use the constant multiple law and kind of factor out per se maybe, or take out that coefficient since it has no effect on the limit. So using the constant multiple law on the first piece, I'll end up with negative 7 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 11. Since the second piece was already good to go, I just need to continue to rewrite that. Now from here, I can actually apply these limits directly. And the reason I can is we know what the limit of any linear function is. That's going to be equal to 5 itself, since on a graph this is representing a straight line going through 0, 0 with a slope of 1. So when x is 5, then my output to that would also be 5, because I'm looking for my y value on that graph. And then plus, if I take the limit of a constant here, this is representing a horizontal line on a graph. So I have a horizontal line technically at y equals 11. So no matter where I'm approaching on that line, the y value will always be 11. So my limit as x approaches 5 then, doesn't really matter what I'm approaching. If I'm just taking the limit of a constant, I will always get that constant out, which is why I get positive 11. Now from here, we could simplify it, but on the AP test, anytime I have a free response problem, there is no need to take the time to simplify it. And the reason behind that is a couple things. One, you're taking a calculus class. You guys can do algebra, you can do all of that stuff already. There's no need to show it per se. The second thing is, honestly, the AP test, it takes a lot of stuff to get through, and you want to make sure you're using your time wisely. So if we don't need to simplify on a free response, there's really no point to, because we want to save our time for other problems that might be more challenging. Then the other reason is, if you were to simplify this, you're allowed to, you can, but if you make a mistake in simplifying it, you will lose points. So you just kind of want to be careful there. You wouldn't want to make a silly algebra error and have that cost you some points then. Okay, let's look at our second problem. It says the limit as x approaches negative 2 of x to the fourth. So I have a power law here because of this fourth exponent. So I can use the power law and rewrite this limit as the limit as x approaches negative 2 still of x with the entire thing raised to the fourth power. So that's that same thing as taking that kind of exponent out of the limit. From here, we can take the limit of this linear function, and that would be equal to negative 2. And then the fourth power is of course still there. And from here, now that my answer is numeric, I'm done. Yeah, I could go ahead and simplify that, but there is no need to have to. Okay, let's look at our third example. Our third example says the limit as x approaches 3 of 2x over x minus 4. Why don't you guys pause the video and try example 3 on your own first, making sure to show all the limit law steps. As we check example 3 now, the first thing I notice is I have this quotient, so I'm going to break this apart using the quotient law and rewrite it as the limit as x approaches 3 of 2x in the numerator, all over the limit as x approaches 3 of x minus 4 in the denominator. From here, I can use the constant multiple rule on top, and the 2, which is our scalar in this case, can come out. So I get 2 times the limit as x approaches 3 of just x divided by, now in the denominator, I can use the difference law, and I can break that apart into the limit as x approaches 3 of x minus the limit as x approaches 3 of 4. Now you want to be careful here. Because I'm using the difference law, I'm not thinking about this as a negative sign on the 4, but instead of as a subtraction sign. So I'm doing the limit of x minus the limit of 4 in this case. If you were to have an extra 4 or an extra negative on the 4, really what you're doing is you're adding 4 then. So I already took care of my negative by making this into a subtraction. So I wouldn't want to also have the 4 be negative as well, because that would actually be changing the problem. Now from here, we can take the limit directly now. We've finished applying all of our limit laws and broken this up as much as we can. So the 2 is going along for the ride as a scalar. I know the limit as x approaches 3 of x is just equal to 3, since x is a linear function, divided by, again, the limit as x approaches 3 of x is equal to 3, minus, now the limit as x approaches 3 of 4. Well, 4 here is a scalar, so again, that's our horizontal line on our graph. So this limit, it doesn't matter what I'm approaching, it's always going to be equal to 4, no matter what x value we are approaching. And again, since this is numeric, I'm going to go ahead and box my answer. There is no need to simplify from there. Okay, let's look at our last example on this page. So example 4 says the limit as x approaches 4 of the square root of x plus 8. So we're going to look at a root law here since I have a square root. So the first thing I'm going to do is apply that, and I'll get the square root of the limit as x approaches 4 of x plus 8. From here, I can break apart this limit using the sum law since I have the x plus the 8. So remember, you still have your square root here, and I get inside the square root the limit as x approaches 4 of x plus the limit still underneath the square root as x approaches 4 of 8. Let me just extend my square root all the way out. Oops. One big long square root. Now remember, if you have the sum of two things or even the difference of two things underneath a square root, I cannot break that apart into two separate square roots added together. Instead, that's the square root of both pieces still added together inside, which is why I have one entire square root here. Now from here, the square root's going to stay because there's nothing I can do with it yet. I can now take the limit as x approaches 4 of x. That's going to be equal to 4. And then the limit as x approaches 4 of 8, again, since that is a scalar, is just going to be equal to 8. Now, if I wanted to, I could go ahead and add the 4 plus 8 and simplify the square root as much as I can, but there's really no need to now that I have a numeric answer. Now let's look at our last kind of group of examples. So in our first 4 up here, what we had was functions as our inputs already. So we're taking the limits of functions, breaking them apart using the limit laws until we got pieces that were the limit of either just x by itself or the limit of a constant. In the next set of examples, what's going to end up happening is we're going to look at more kind of abstract functions here. So I have this limit as x approaches 1 of 2 times f of x, where they're not going to tell me what f of x is. And this is a common thing on the AP test. Instead, they're going to give me information about the limit of f of x and the information, as well as the limit of g of x and the limit of h of x. So I'm going to go up here and kind of keep track of these by highlighting each of these. So I know that the limit as x approaches 1 of f of x is going to be equal to 7. I know that the limit as x approaches 1 of g of x is going to be equal to 5. And our last piece says the limit as x approaches 1 of h of x is going to be equal to -2. This is a very common type of AP question where they like to give you pieces of information but not actually tell you what the functions are. And so one thing I do want to point out is I don't know what f of x is equal to g of x or h of x, and that's fine. I will have enough information to be able to answer these questions down here if I'm using the limit laws correctly. So let's look at our first example. So it says the limit as x approaches 1 of 2 times f of x. Well, the first thing I notice here is I have this scalar. So using the constant multiple law, I can take the 2 out and I get 2 times the limit as x approaches 1 still of just f of x by itself. Well, remember what we were given. We know what the limit as x approaches 1 of f of x is equal to. They gave that to us at the beginning part of the question. And what I'm going to do is replace this entire limit as x approaches 1 of f of x with the answer that they kind of gave us up at the beginning of the question. So that limit as x approaches 1 of f of x is going to be equal to 7. So the 2 is still going to be there, and I'm going to replace that whole piece with the 7 then, since I know that that limit of f of x is equal to 7. Now that my answer is numeric, there is no need to go ahead and simplify. I am good to go. So although we never knew what f of x was equal to, I didn't need to for this question since all of the questions are about limits and I can evaluate them using the given information. I'm going to have you guys go ahead and pause the video. I want you guys try example 6 on your own first, making sure to show all of your limit law steps. All right, let's check example 6. So example 6 says the limit as x approaches 1 of g of x plus h of x. So I have a sum law here since I'm adding g and h together. So I'm going to go ahead and break this apart as the limit as x approaches 1 of g of x plus the limit as x approaches 1 of h of x, since I can do that using the sum law. Now from here, I know what each of these two pieces are equal to. We know that the limit as x approaches 1 of g of x is equal to 5, so I'm going to replace that with a 5 since they gave that to me, plus the limit as x approaches 1 of h of x, they also gave that to me, is equal to -2. So I get 5 plus -2, or if you want to write it as 5 minus 2 would work as well. Since my answer is numeric, I can go ahead and box it because I'm good to go. Okay, example 7 says the limit as x approaches 1 of f of x times h of x. So using our product law here, I can go ahead and break this apart into the limit as x approaches 1 of f of x times the limit as x approaches 1 of h of x. And since we were given what each of those limits individually are equal to, then this is equivalent to, instead of saying the limit as x approaches 1 of f of x, I can replace this first piece with 7, since I know that that is equal to 7, times the limit as x approaches 1 of h of x, we know is equal to -2. Now that my answer is numeric, I am good to go, and I can go ahead and box that. Okay, looking at example 8, we have the limit as x approaches 1 of the square root of g of x. So I can use the root law here and break this apart instead into the square root of the limit as x approaches 1 of g of x, all inside the square root. And now we know what this limit as x approaches 1 of g of x is equal to. That's equal to 5 that they gave me at the beginning. So I end up with the square root of 5 by replacing what this limit is equal to then. Now that my answer is numeric, again, I am good to go. Okay, let's look at example 9. I want to try to leave the information at the top for us to use there. So we have the limit as x approaches 1 of 3 times h of x all over g of x. Why don't you guys go ahead and pause the video again and try example 9 on your own first. Okay, let's check example 9. So the first thing I notice is I've got two things going on. I have this 3 in front of the h of x, so that will be a constant multiple rule that I'll use, but I also have this division bar. And I'm going to have to use the quotient rule first since the 3 is only being multiplied to the h. So I've got to make sure I'm kind of taking this apart in the correct order here. So I'll get the limit as x approaches 1 of 3 times h of x in the numerator all over the limit as x approaches 1 of g of x in the denominator, using our quotient law from there. Now the last step I have to do before I can apply what was given is this 3 as a constant multiple can come outside of the limit, and so I get 3 times the limit as x approaches 1 of h of x all over the limit as x approaches 1 of g of x. From here, since I have the limits of each function kind of on its own now, I can go ahead and just substitute in what they're equal to. So I still have the 3, and we know that the limit as x approaches 1 of h of x was equal to -2. That was given up top. All divided by, we know the limit as x approaches 1 of g of x is equal to 5. So I can go ahead and sub that in as well. Now that my answer is numeric, again, I am good to go with all of these from here. So in these last 5 examples, we kind of saw, well, what happens if we don't know exactly what our functions are equal to, but we know information about the limits of those functions? How can we apply the limit laws from there on something that's a little bit more abstract? The last thing I want to talk about is some takeaways that's not only true for this section, but just kind of in general. So the first thing, and we've talked about this in past videos, is that notation is extremely important. Okay, we have to make sure we're using our notation correctly. We can't have any floating limits without inputs into them. We talked about that a lot in the last video about the graphs of limits. We just really want to make sure that our notation is being precise and correct as we go through these. And this is going to continue on throughout really the rest of this course, especially in one of our next videos, which is going to be about continuity. And that's going to be a big thing there. The next thing is that we learned for the first time that simplifying on free response is really not necessary. Once our answer is numerical, we are done. And what I mean by numerical is, in this past example, once I got rid of all the limits, so the limit as x approaches 1 of h of x, once I replaced that, and I replaced the limit as x approaches 1 of g of x, and I got to kind of what I boxed over here, and I just have a bunch of numbers that are added, subtracted, multiplied, divided, that's fine. I don't need to simplify the arithmetic. But once I have numbers, my answer is numerical and I'm good to go. Now the last thing I want to point out kind of leads us into continuity, and it says that the limit as x approaches 1 of f of x equals 7. So remember, we were given this up above. That was the information we were given. This does not necessarily imply that f of 1 is equal to 7. And that's a common misconception that a lot of people have. And I can see why. It's tempting to want to say, well, wouldn't it just be a direct substitution? So f of 1 has to equal 7. And that is not necessarily going to be true at all. So this is leading us into continuity that we will talk about. And this is a very important distinction here, is just because the limit exists and is equal to that number does not necessarily mean that the function value is equal to this. And one example I want to show is kind of from a graph based off of our last video. So if I were to graph this, this says the limit as x approaches 1 of f of x equals 7. Well, what this truly tells us is that if the limit exists, then going back to our definition of a limit, it means that the limit as x approaches 1 from the left-hand side of f of x has to equal the limit as x approaches 1 from the right-hand side, which must equal 7 then, because that's how we get a limit to exist, is that the left-hand limit equals the right-hand limit. So if I were to graph this, I'm going to let's put 1 there. For the sake of it, I'm not going to draw a bunch of tick marks. I'm just going to label 7 up here. All that I know right now is I don't know what's going on in the rest of this graph, but I know, let's say this squiggle line comes in. Oops, hold on. I want to make sure it still passes the vertical line test as a graph. But what I know is I have some graph over here doing something, some graph over here doing this, and that they are meeting as x approaches 1 from either side here. So as I come in from the left-hand side, I'm approaching 1 and it's equal to 7. As I come in from the right-hand side, as x approaches 1, I'm also equal to 7. That's what this first piece of this limit tells us. It does not tell me that that circle there is necessarily a closed circle. That's what this f of 1 equals 7 would mean, is that, and I'm going to go ahead and circle that in a different color, is that f of 1 equals 7 would mean that there's a filled in circle, but there's no way to know if that circle is filled in or not just based off of the limit. And in the last video we talked about with the graphs of limits, we saw a lot of examples where just because the limit from the left equaled the limit from the right did not mean that the function value was necessarily equal to this. So this piece that I've circled in green, remember, is the function value, or the closed circle, and I don't necessarily know where that closed circle is going to take place on the graph. And so although it's very tempting to want to say, well, the limit is equal to 7, so f of that number has to be equal to 7. That is not necessarily true. There are cases where it does happen, but it's just not guaranteed at all. And we're going to talk about the relationship between the two and what happens in this case when they're all equal to the same number. We say that that function is continuous, and we'll be talking about that as we go on in this course. And continuity will be a very important key thing. This is just something I want to bring up now, especially as we saw this more abstract examples with examples 5 through 9.